the things that we're going to cover in this video are just related to standard S2 still. This first part, the difference of square factoring patterns, that is still something that you have to know to get proficient. So this is still part of a 3-type problem. And then we'll look at the 4-type problem. Alright, so there's many factoring patterns that occur just depending on the kind of numbers that you have and the kind of setup. The only one that I make you memorize at this point is the difference of squares factoring pattern, which looks like this. And before we actually start getting into that, if I gave you a problem that looked like this, and we factored it the way that we've been doing, we would start by multiplying a and c together to get negative 36, and then I need to look for two numbers that multiply to get negative 36 and add to get 0, because I'm missing my bx term. So those two numbers would be positive 6 and negative 6. So then I'd replace that 0bx with those two numbers. Plot a 2x. Plot a negative 3. So I get 2x minus 3 and 2x plus 3. Now, something that I want you to notice is that your first term was 4x squared. The first term, both parentheses here at the bottom, is 2x. Well, 2x is the square root of that. And then my second term was a 9. Square root of 9 is 3. That pattern will always happen when if you're subtracting two things that you could take the square root of, which in this case you can. You'll always get two parentheses that look exactly the same, except one's positive and one's negative, and the terms in them are square roots of those two. So instead of having to do all this work every time, if you notice, hey, I have a difference of squares, then you can shortcut and go from this step to this step. Okay, so that's why I have you do this factoring pattern, because if that scenario is what's going on, let's do 3 examples here, then it's going to be a lot quicker and faster to use the pattern. So let's say we start with 121x squared minus 144. Okay, first thing I recognize, hey, I've got a subtraction. Next thing I recognize is, hey, I can take the square root of 121 and of 144. So if we're going to follow this pattern here, the a and the b represent the square roots of both those terms. So a in this case would be the square root of the first term, which is 11x, and b would be the square root of 144, which is 12. Don't worry about the negative because the pattern takes care of the negative. And so your factoring will be same exact thing in both parentheses, just one's positive and one's negative. And you can always double check. If we were to refoil this, 11 times 11 would give you 121x squared. Outer and inner would cancel, and your last terms, negative 12 times 12, would give you negative 144. And that will happen every single time. So let's look at 9x squared minus 49. Again, same type of deal here. You can take the square root of both the terms. You have two terms, and you're subtracting them. So it fits this scenario of difference of squares. Your a and your b will be the square root of both those terms. So square root of 9x squared is 3x. The square root of 49 is 7. And then when you go to factor, it'll be the same thing in both parentheses, just one's positive and one's negative. Let's try this one. Okay, now when I look at that, I don't think difference of squares right off the bat, because you can't take the square root of 3 and have it be what we call a nice number. You can't take the square root of 27 and have it be a nice number. But what I can do is take out a 3 and then look again. And in this case, yeah, I can take the square root of x squared. That's x. I can take the square root of 9. That's 3. So then that becomes x plus 3 times x minus 3. And since I'm not solving, that 3 I pulled out, I'm going to include in the very beginning of my answer. Okay, so 3 quick examples. I mean, we're going to talk about this more tomorrow and practice this more tomorrow, but 3 quick examples of this particular factoring pattern that pops up a lot. It'll pop up again next unit, which will help us with factoring and solving quartics and cubics, so make sure that keep that in mind. Okay, now these are going to be 4-type problems. I'm probably going to keep this one to go through with you, because I didn't want this video to be super long for you tonight. Example 6, factoring quadratic with complex roots. If I'm given something, or I give you something like x squared plus 9. Maybe that's not the example I want. You know, I think I'm going to come back to this one too tomorrow, just because I need to revisit how complicated I want those to be. I need to look back at the my standard sheet. I don't have it handy right now, so those won't take us too long. I mean, it's doing the same factoring. It's just meaning you're going to have some complex roots involved instead. So we'll come back to that one. All right, so let's look at example 7, because this one is going to be where I want to focus tomorrow anyway. Example 7, and maybe we'll do example 8. Billy made a rectangular piece, or has made a rectangular piece of sheet metal that's 5 feet by 4 feet. You want to make a frame for it using 10 square feet of extra wood laying around. The frame should be of uniform width. What should the width of the frame be? Okay, so we have this scenario going on where you want a border. You know that this side, that sheet metal in the middle, maybe that's the 5-footer, and here's the 4-footer. And it says it wants it of uniform width. And since I don't know what that uniform width is, I'm just going to label it as X. And then what should the width of the frame be? Well, in this case, the way I've set up the problem, the width of my frame is labeled as X. So let's just see if we can set this up. Another piece of information that it gave me was this, which represents an area. Oh, and they kind of give me the area there, too. So when that happens, you know you're going to be looking at an area equation. And I'll give you a hint here. With quadratics, the height of something that goes to the area is one way that quadratics is used often. But area of something is another. Like when you talk about the square footage of a room, you're like 5 by 7. Or if you're talking about the actual carpet that you lay, it might be 7 feet squared. Or something. That's a really small room, but 7 feet squared. So when you're talking about area, you're talking about the units being squared. So that makes sense that quadratic would then model that. So that's kind of what we're going with here. So since we have a square rectangular type figure, I know the area of that figure is going to be length times width. Okay. And then we have two different pieces here that we're going to have to pay attention to. But let's look at the whole piece first. So the length we can write as 5 plus 2x, or 2x plus 5. The width I can write as 2x plus 4. And then I need the area of the whole thing. But the area of the whole thing is this piece, which is 20, because 5 times 4 gives me 20. And then of the border, which it told me it has 10 square feet. So total, the area of the whole figure is going to be 30. Okay, so here's my setup. Now to solve for x, I'm going to have to simplify first, because I have to be able to get everything over to one side and get it equal to 0 in order to try to solve. So I'm going to FOIL that part out. So you get 4x squared plus 8x plus 10x plus 20. If I FOIL that out, and then I'm going to subtract 30. All right. And now I'm going to try to pull out a greatest common factor, which it looks like 2 is my greatest common factor. So I end up having 2x squared plus 9x minus 5. Okay, so I'm going to start this problem by multiplying my a and my c together, because now my goal is to try to factor and solve. So I get negative 10. The two numbers that multiply to get negative 10 and add to get 9 would be 10 and negative 1. So we have 2x squared plus 10x minus 5. Pull out a greatest common factor of 2x here. We can pull out a greatest common factor of negative 1 there. So you get 2x minus 1 times x plus 5. And you get 1/2, or negative 5, as your two solutions. The one that makes sense here, though, because we're talking about a length of some sort, is going to be this x value for 1/2. So the width of the frame is going to be 1/2 of a foot. All right, checking the time here. All right, I think that will be where we stop. And tomorrow we'll talk about example 8 after we practice this one. These will be the two that we focus in tomorrow together in class, and then practice these also.